calculate, since we now know the value of x, we can actually calculate how much got lost. And so,
Yeah, what were you looking for?
how far would it compress was the original one?
Oh, okay.
But we could do how much energy was lost. So it would be 0.3 times 8 times 9.8 times the cosine of that, which is about 0.6, times 5 plus our 6 over there, so 11.75. 75. And this will be some number that's just absolutely amazing.
Is it? Oh, whoa, never mind. 166.32.
What did you get, 253 first?
No.
So it loses 166.32 joules. Again, this gets down to the semantics of the question. If I ask what's the change in energy is negative 166.32 joules. If I ask how much energy was lost, 166.32 joules was lost. If you said negative 166.32 joules was lost, that's like a double negative.
So wait, that's our coefficient of friction, mass, mg, and then h, 11.75 x.
This is how far it went, that's the distance, and that's the force.
Oh, so you just did, you just calculated energy. Yeah, that one.
And that is a plus sign now. All right, questions to hear?
Wait, did that 11.75 come from 5 plus 6.75?
Yes.
Okay.
Because the friction was acting on it for the entire duration before it hit the spring and then after it hit the spring. All right, here we go. I'm going to erase this. And we're gonna start whatever the next chapter is. We got time.
For like 5.
Yeah, we got time.
We got 8. We got
7 minutes.
We got 2 minutes.
If you recall, when we started the work energy bit, we started with the two items that were colliding, and I said, what are the 3 things in common? This time, we're gonna, instead of looking at the force and the displacement, we're gonna look at force and time. So I'm just going to, I'm not gonna set to, actually, sorry, I will. So I know that the force on A from B is equal to the negative force on B from A. So we start out with Newton's third law.
New page.
The time that they both interact with each other is the same, so I'm gonna multiply by the time. We'll make it some infinitesimal amount of time, and then we'll integrate. Newton's second law, what is force equal to? So we have mass of A times the acceleration of A dt is equal to mass of B times the acceleration of B dt. Integrate.
Negative.
Because Newton's third law is true over the entire duration of hitting each other.
Yeah, negative mass.
Thank you, there's a negative here. This is from some initial time to some final time. And if I integrate, mass is a constant here, so we assume these things are not spontaneously combusting. So mass will pull out of it. So I have mass of A times the integral of A dt from some initial to final time is equal to the negative mass, and this is of A, negative mass of B, negative mass of B times the integral of A sub B dt from some initial to final. So what is the integral of A dt?
Velocity.
And so if we take velocity from the initial to final, that's basically, that will be final velocity minus initial velocity.
1/2 mv squared. That is, okay.
So we end up with, I guess officially, velocity from some initial to final. So this becomes mass times V final minus V initial, which is mass of A. Of course, too low. So mass of A times V final minus mass of A times V initial equal to, we do the same thing on this side, negative mass of B, oh, that's VFA and VIA. Mass of B times V final of B minus mass of B times V initial of B. Distribute the negative sign. So we have mass of A, V final of A, minus mass of A, V initial of A equals negative mass of B, V final of B, plus mass of B, V initial of B. At this point, physicists just get tired of writing the same thing over and over again. So instead of writing it, since MV shows up 4 times, why don't we just come up with a new letter? How about P? And we'll let P equal MV. It is a vector. So we have P final for A minus P initial for A equals negative P final for B plus P initial for B. So all we did was just from here to here, just substitute this single letter instead of the 2 letters. At this point, we're going to get the initials on one side, finals on the other. So I'm going to pull this over to this side and that to this side. So if P final of A plus P final of B equals P initial of A plus P initial of B.
So we'll have this, right? We won't have to go through all this ourselves.
As in, I can ask you to regurgitate this?
Yeah.
No, I'm not going to ask you to regurgitate
So
it.
this is basically.
What I want you to know is where this stuff comes from.
Okay.
So just a proof, right?
Pardon?
It's just proof.
That's it, yeah.
You know, or derivation.
Theorem.
All right. So what we have here, this is the kind of thing that makes physicists' hearts go all at Twitter. We have this quantity called P for right now, that if I add up the total afterwards, that's equal to the initial total. That is a conservation law. As any of you in here who's had physics before, probably already know what P represents.
Momentum. Yeah.
Washington.
And this is sort of the derivation of conservation of momentum.
I remember momentum. It was something. It was definitely.
This has the supreme advantage over conservation of energy in the fact that we are dealing with vectors, so we do not lose direction in the equations. And obviously, it has the disadvantage over energy in the fact that it involves directions. Now, we can apply conservation, we can apply what we're dealing with here with momentum to all the stuff we've done already, but there are certain cases in which using momentum actually makes a lot of sense. And the time that you will definitely be using conservation of momentum is during collisions. What I want you to do is when you think collisions, think, conservation of momentum. I will define more specific types of collision. There's perfectly elastic, perfectly inelastic, and imperfect collisions. We'll get into that, but I will tell you right now, on the last test, there will be a perfectly elastic collision and a perfectly inelastic collision problem on there,
Final?
on the final test.
Okay.
The one, April 30th, I think it is.
Yeah, that's last day.
Two tests.
30th. Can't wait.
Test 3 coming out.
Some final note, one other thing.
The day after that.
If we look at the left-hand side here, we eventually get down to this point right here. This is just the change in momentum. And it all starts from this right here. This has a special name. Anyone happen to know what it is? Because I have an obscure clue. What I will call my most obscure clue.
Fluid.
Was that?
Fluid sailing.
You're saying that,
I'm saying that oh, sorry, babe. Slightly off there. The integral of f dt is equal to the change in momentum. This f dt. When someone suddenly buys you flowers, that's called, this is the obscure clue.
Surprise.
Yeah. Not what the physicists went for.
An apology?
If only they had called this an apology.
A gift.
The reference, it's a 70s perfume commercial. So all of you remember the 70s.
The show, yeah.
Yes.
kinetic energy is 1/2 mv squared, and this is mv.
Yes.
So the derivative of 1/2 mv squared is mv.
No, that's M2.
As if you do dkdv. Yeah.
Back to the point.
By the way, this is impulsive. If someone suddenly buys you flowers,
Oh.
that's impulsive.
Oh.
That's impressive.
Let me hand back, I got some stuff to hand back. Chapter 5 quiz and master sets. Russell. I can turn that off.